We are going to start talking about the next chapter. The previous chapter was all about closed sets and closures, and then also interiors and boundaries. The next thing we're going to talk about is a chapter about creating new topological spaces out of existing ones. Maybe I'll call this building new topological spaces. Building new, it looks like mu. Building new topological spaces. This is like if you have two topological spaces, can you somehow like combine them together and make a new one out of them by doing, I don't know, the union or the product or something like that? Actually, the union is not very interesting, but there is something interesting called the product topology. If you have two different topological spaces, you can make the product of them. There's also a quotient, and there's some other ones that we're going to talk about. That's the theme of the next chapter, creating new topological spaces out of existing ones. The easiest one of all of these is where we're going to start, and that's not one which, not any of the ones that I mentioned already. The simplest one of these is easiest to create a subspace. That is, if you have a big topological space, you can consider only part of it, and that part of it makes its own topological space. Now, this is a little tricky to do because it doesn't, a subset of a big topological space does not automatically become a topological space on its own. It's not like a subgroup. You know, if you have a group, if something is a subgroup, then you use the same operation on it and it has the same identity and all that. The subspace topology is not so straightforward as that, but it's not very difficult. The situation you should imagine is, you know, we have R2, that's like the big space, and if you have a set inside of R2, I'll draw some kind of blobby thing here. I'll call that Y. Y can sort of inherit the topology from R2 to become its own space. All right. Now, like I said, it's a little, I'm imagining Y has the inside points also, although I suppose it doesn't really matter. There's a little bit of subtlety to this because remember, a topological space itself, the entire space is always open and closed, right? Whereas on this picture, it looks like Y is closed but not open because it includes all of these boundary points here. So as a set by itself, Y is not an open set, but we can turn it into its whole space, and then it automatically becomes open and closed. So there's something a little strange that has to go on in order to make this work, but this is the idea. Y can just become a topological space by using the same neighborhoods that you get from R2, more or less the same. Anyway, here's the definition, and then we'll just talk about what this looks like in practice. So let X be a topological space, and Y is a subset of X. And then I'm going to tell you how you can make a topology on Y. So then we say, I'll call this T sub Y. You imagine you already have some topology for X, some bunch of open sets on X. Then the topology on Y is defined to be U intersect Y such that U is open in X. All right. This is the topology that we use on the subset. And let me just finish writing some words here, and then we'll talk about what this intersection really means. So this is a topology on Y, and it's called the subspace topology. All right. And if you have a set which is open in this topology, so sets in this thing, ty, are called open in y. All right? If I say a set is open in y, it means it's open in the subspace topology. It might not be an open set from the original larger space, but it is open in the subspace topology in y. All right, so for example, I'm going to try and draw another picture here. What if my set looks like, you know, some kind of a weird creature like this? Maybe it has a hole in it here, has some hairs. All right, here's my set, including all of these points on the inside. This hairy thing. All right. And this is as a subspace of R2. All right, so using the standard topology from R2, you have this thing which is inside of R2. What are the open sets in that thing when I consider that thing as its own topological space? An open set, and what the rule here says, it's an open set in Y. That's this weird thing is my Y. It's an open set in Y. What that means is they are sets that look like U intersect Y, where U is open from X. So when I'm trying to think about what do the open sets here look like, what they look like are open sets from R2 when you intersect them with Y. So for example, here is an example of an open set in here. I'll big up my picture a little bit. If I just take something like that, that is an open set in Y with the subspace topology, because an open set looks like an open set from R2 intersection with Y. All right, that's what this TY definition you can see up there. U intersect Y, where U is an open set in R2. And this here, it just looks like an ordinary open set in R2, but you intersect it with Y. That's already inside of Y, so you get that whole thing. All right, that's what a neighborhood in Y looks like. Now, things get a little weird close to the edge because of this intersection. So that's one example of what an open set could look like. What about right on the edge here? Here's another example of what an open set could look like. This. All right. That would be a set. Again, this is the intersection of an original open set from X, which would be like the entire circle, right? But you only take the part of it which is in Y. That's why I only took sort of half of that. All right. So this blue thing is also open in Y. I'm trying to draw examples of sets which are open in Y. All right. Using the subspace topology from R2, the open sets more or less still look like filled in balls, but the ones that are right on the edge, sometimes they look like sort of a half a ball because it's a ball intersected with Y. All right. And there's actually other weird things that it could look like in this particular example. If you look on one of the hairs, what could an open set look like there? Well, it would look like a ball from R2 intersected with the hair. And what that would look like would be just sort of a line segment within the hair, right? That's what it would look like if you took a ball from R2, but intersect it with the hair. What you get is actually, to be specific, it's kind of like an open interval in here, right? Not including its endpoints, because it is the result of intersecting an open ball from R2 with the hair. All right, so that sort of open interval-like thing is also open in the subspace topology. All right, and maybe one more example of a weird thing. Actually, I got two more. What about if I took a neighborhood again on the hair, but right on the end of the hair? All right, then it looks like, again, it looks like a ball from R2 intersected with the hair. That would look like something like this, where it's missing the endpoint where it intersected the ball, but actually it includes the other end of the hair, just because that other end was inside the ball. All right, so that could be an open set. And then one other thing would be, there are weird looking open sets right where the hair meets the the blobby part, that would be something like, like right around this point. What does an open set around that point looks like? Well, it looks like an original open set from R2 intersected with that. So what you would get would be sort of this bottom of the circular part and also this part of the hair, not including that endpoint. All right, so that's another weird looking neighborhood. All of these things are the open sets in Y. All right. Any questions about that? They are weird, slightly weird, I suppose. They are more or less like balls from R2, but they are intersected with Y every time. Those are the neighborhoods in Y with the subspace topology. All right. Can we discuss briefly? I would like to actually demonstrate that this really is a topology. I don't know, maybe you missed, we did this a lot in the first couple days of class. Can you demonstrate that is a topology? That involves showing the three properties of what it is to be a topology. I hope you remember the first one is just that the empty set and the whole space are open. The second one was finite intersections of open sets are open, and then also any union of open sets is open. Can we try and work that out? Let's demonstrate. So maybe I'll write this as a theorem here. Ty, I will copy the definition again. It's defined to be U intersect Y where U is open in X. The theorem is just this is a topology on the set Y. All right, and we have to demonstrate the three properties. So the first property is empty set and Y are open. All right. How do we demonstrate that the empty set and Y are open? Well, what it means to be open in the subspace topology is that it's some open set from X intersected with Y. So we must write. Can you write the empty set as something intersect Y? Because if you can, then that makes it open. Where the something is open in X. Any thoughts about that? Can you write the empty set as something intersect Y?
Say empty set?
Yeah, the empty set, right? Actually, it's going to have to be the empty set. If you want to get the empty set from the intersection, you better have the empty set here. So yeah, the empty set is empty set intersect Y. And empty set, this is open in X, right? And so that means empty set is open in Y. Because it is something intersect Y where the something was open from X. All right. And what about, so that's half of it, right? We have to show that empty set is open in Y and also Y is open in Y. Okay. Try and do the same thing. Y equals something intersect Y. Fill in the blank here with an open set from X. This one's a little trickier, maybe. I don't know. You might be tempted to just say Y there, because it's certainly true. Y equals Y intersect Y, but actually, don't say that because this is not open in X, not necessarily, right? Like in my weird example, this Y is definitely not an open set from X. You have to put something in this position which you know is open in X. An idea?
The interior of Y.
The interior of Y? This is a good idea, but actually it's not true that Y is equal to the interior of Y intersect Y. If I put a little IKEA on that, I don't know what that accent is actually called. Does anybody know? I shouldn't just call it the IKEA accent. IKEA has other weird things that they say too. That's not true because the interior might be smaller than Y, and so it is not necessarily true that this equals Y. Any other idea? That was a good idea. Yeah, you have to make something which is open in X. That's the thing. So interior is good in that sense, but perhaps, yeah?
Can you just choose X?
X. Yeah. This is a great idea. X, the entire set. Would you agree that y equals x intersect y? Yeah, x is everything, like the whole big space. And then if I only take the things which are in y, that certainly does equal y. And now that is open in x, right? That's part of the definition of the fact that x is a topology, or that x is a topological space. So the whole space x is open in x. All right, so here we conclude y is open in y. All right? And this actually gets around this weird issue. Remember I said before, it is a little weird, and this is just something you have to become comfortable with. Y by itself is not an open set in R2 because it has these weird hairs, and it includes all of these boundary points. So it's definitely not an open set in R2. But Y, when regarded with the subspace topology, Y as a space by itself, it is an open set when regarded as a space on its own. This is a little strange and sometimes confusing, but that's how we do the subspace topology. All right, that was the first part. Can we do the next, the others? All right, this is the finite intersections property. All right, so we need to say something like let U1, etc. to UN be open in Y. And then I want to show that the big intersection UI I equals 1 to n is open in Y. Right? This is how you show the finite intersections property. So, what do we know about the U's? You got to say something about the U's. Since UI is open in Y, what does that mean to be open in Y? It means it is an intersection of something in open in X intersect with Y. That's the definition of what these opens means, right? So since UI is open in Y, we have something like UI equals VI intersect Y for VI open in X. This is the definition of what it means to be open in the subspace topology. It means that your open set is actually the intersection of some open set from the larger space intersected with Y. All right, can we do some magic with this then? So this is, I'm just going to sort of plug that into here. What I want to show is something about this big intersection. So I can say intersection of UI, I equal 1 to n, is actually intersection of VI intersect Y, I equal 1 to n, right? Can we simplify this at all or rewrite this somehow? This is a big intersection of individual things being intersected with Y. Anybody feel like we should be able to rearrange this? You could say this is the set of all the points which are in all of the all of the VIs and also in Y, right? Or it's in all of the VI intersect Ys. I believe this is the same as this. Right? They're both two ways of saying all the points which are in Y and also in all the V's. Right? This says all the V's and also in Y. This says in Y and all the V's. I mean, it's the same set. All right. Anything to point out here? I would like to point out here each individual VI is open in X, and here I have an intersection of VIs. So this is open in X. This part here is open in X. That's because X is a topological space, and so the finite intersection of open sets from X is also an open set from X. And what does that mean? Yeah.
If it's open in X, would it be open in Y also?
Yeah, that means this whole set, so like that piece of it is an open set from X, which means this whole intersection is open in Y, because that's what open in Y means. It means a piece which is open in X intersected with Y. So this is open in Y. And actually that's what we needed to show, right? That was the whole thing here. I said we want to show that this intersection is open in Y. And that's what it is, right? The original intersection. You do this, you rewrite the set, and I have something open in X intersected with Y. All right? That was the finite intersections property. Why does the intersection have to be finite? This is always something that is, you can always ask yourself. Would this have worked even with infinite intersections? Well, it had to be finite just because I used this fact right here, this fact that this intersection is open in X. That's because X is a topological space, so the intersection needs to be finite in order to do that step. All right? This was the intersections property. How about the unions property? It's actually more or less the same. So this is about any unions. Although because it's not finite, you have to write it slightly differently. You probably remember this from when we did homework maybe 2 times ago. I don't think you had to do this last time, but we say something like, let U alpha be open in Y for all alpha in A. So it's not 1, 2, 3 up to n anymore, because it's possibly infinite, possibly even non-countable. So you have to just say, I just have a bunch of open sets. They're not necessarily 1, 2, 3. They're just a bunch of open sets. All right, and then what I want to show union alpha in A, U alpha is open in Y. This is what we want to show. All right, and how we do, we say, all right, let's just consider. No, before that, I'm going to say since U alpha, really it's the same steps as the previous argument. Since U alpha is open in Y, that means we have U alpha equals something like V alpha intersect Y for V alpha open in X. This is what it means to be open in Y. It's something from X intersected with Y. And then we can say union of all the alphas, U alpha, is, I replace the U's with V alphas first. V alpha intersect Y. So this is taking together V alpha intersect Y, all of them together. But this is the same, again, by some kind of rules about unions and intersections. This is the same as all of the V alphas taken together and then intersecting with Y. And now I say this is open in X because it's a arbitrary union of open sets from X. So this is open in Y. Same proof, really. This is the subspace topology. All right. Yes?
Do we use the alpha because it's infinite?
Yeah, because it's infinite, and furthermore, maybe not even countable. So you can't do just like 1, 2, 3 up to infinity, because that would be countable. So you have to use this set A might be infinite, it might be uncountable. So you can't ever say anything like U1, U2, U3, U4. It's a slight notational inconvenience. It usually doesn't make a difference in the proof, really, but you really shouldn't write it with 1s, 2s, 3s, 4s. All right. Great. I would like to look at a few more examples, just some more pictures. There really isn't a whole lot to say about the subspace topology. We're going to be talking about the subspace topology all the time, but like I don't have any sort of big theorems to prove about the subspace topology. Let's just look at some other examples here. Yeah, how about, so I got some fairly simple example and then some weirder looking ones. How about, again, subspaces of R2. How about Y is just the circle? That is like the outer edge of the circle, not including any of the endpoints. I would like to ask, what does a neighborhood in Y look like? Really, I'm asking, what does a basis neighborhood, like a small neighborhood, not a, obviously the whole set is a neighborhood, it's open in the subspace topology, but I don't want to talk about that. What does a basis neighborhood look like in Y as a subspace of R2? You have to imagine what it looks like. This is just like the picture we had at the beginning. What it looks like is a ball from R2 intersected with Y. Can somebody say in words what kind of a set that looks like? If you imagine a ball from R2 intersected with Y. A little ball, because I'm talking about like a small neighborhood.
Is it just like a point on the circle?
A single point? I don't think it could be a single point. You have to think of a ball from R2, which is, like one of these, and then intersect that with the circle at some point. I don't think you can just get one point.
A little bit of the circle.
A little bit of the circle, yeah. Yes, I was hoping you'd use a word other than bit, but I'm not sure if there's a better. Yeah, a little bit of the circle. Like I was going to say something like a little interval inside the circle, something like that, right? To be specific, since I'm talking about intervals, does the bit include the endpoints or not? It does not. Yeah, remember, it comes from intersecting one of these open balls with the circle, and so that the little bit does not include its endpoints. It's kind of like an open interval inside the circle, right? Yeah, great. So what does a basis neighborhood looks like? I would say it looks like a small open interval, right? I say basis neighborhood. Of course, not every neighborhood, not every open set looks like one of these open intervals, because the union of two of those intervals is another open set. So it's not true that every open set is one of those neighborhoods. That's why I stuck the word basis here. All right, all the neighborhoods, all the open sets can be made up of unions and intersections of those little bits, like a small open interval there. What about, let's go sort of one dimension higher. Can we do that? How about in R3, let's look at the sphere, by which I mean just like the outer shell of a solid ball, so not including the stuff on the inside. This is a sphere. What does a neighborhood in there look like? So this time you have to imagine, what does it look like when you intersect this with an R3 ball? An R3 ball is a three-dimensional solid ball without its outer shell. How would you describe what the what a little neighborhood looks like here? Yeah?
A warped plane on the outside with the endpoints not included.
With the endpoints not included. Yes. She said like a warped plane. I am imagining if you intersect this with a round ball. You said plane. I don't think it's not going to be rectangular though, right? It's actually, I would say it looks kind of like a circle, like a circular patch on the surface of this thing. All right, so I would draw that like, it looks like a little Death Star now. That's the laser part. All right. That's it's a circular patch, so it's like a round patch not including its endpoints. I mean, not including the boundary points. Yeah, great. How about, I got a weirder one. You're going to love this one. Topologists like weird examples, and you've seen some examples so far of weird things. How about y equals the infinite comb that you saw in the homework? I don't know if you liked the infinite comb as a subspace of R2. That, if you recall, looks like you get a horizontal line at the bottom across the interval from 0 to 1. And then you also get vertical lines on every point that looks like 1 over n. I'm going to try to draw this nicely if I can. All these vertical lines, and they're all the vertical lines are supposed to go up to the same height. I didn't do that very nicely. And they kind of, come on, it's snapping. I don't want it to snap. Don't do that. All right, I can't make it not snap. All right, and these lines, you know, there's infinitely many lines here, but you do not include the line on 0, right? It's only on points that look like 1 over n's. So these are vertical lines at x equal 1 over n. That's the infinite comb. And if I think of this as a subspace of R2, I would like to ask about what could the neighborhoods look like as a subspace of R2. So now the basis neighborhoods, when I say that, really what I mean is just like a really small neighborhood. I'm not trying to think about large open sets, which could be unions of different intervals or whatever. I just think about the individual little neighborhoods. Basis neighborhood looks like, actually there's a few different types that it could look like. For example, if I picked a point right here, its neighborhood, what does a little neighborhood of that point look like? It would look like an open ball from R2 intersected with the comb. And what would that look like? It would look like a little interval right here. All right? If you took a ball from R2 and intersected it with the comb, what you get is a little open interval like that around that point. All right? So some neighborhoods look like, I'm going to try and draw like a little list of what the basis neighborhoods look like. They could look like horizontal little sort of open intervals. All right? What else could they look like? Well, you could also get vertical type little open intervals, right? At the going up the vertical ones. You can have, this also counts as an open interval in as a basis neighborhood. Okay, so a basis neighborhood looks like that, or this, right? Anybody else see where you could get a basis neighborhood that looks different from either of those? Yeah.
Could it look like perpendicular, like at the base of the line?
Yeah, if you look at one of these points where it actually sort of meets the vertical part, meets the horizontal part, what would a neighborhood around there look like?
Like three.
Like a,
Yep.
yes, she's giving me this
Upside down T.
the sign, like the perp sign in linear algebra.
Yeah.
It's like this. Yeah, like that. That would be if you focus on a neighborhood of one of those points. You get one of those guys. A perp, a turnstile. Sometimes that's called a turnstile, that symbol. Any other thing it could look like? Yeah.
If you put it like close to 0 and then a little above, it could look like a circle of, intervals maybe.
Close to 0 and a little above, like, yeah, this is interesting to think about. If I look, say, around, say, this point right here, I would say actually you can make the neighborhood small enough so that it doesn't include all the rest of these guys, right? Actually, up here, you can always make the neighborhood small enough if the radius is, say, less than, if this point is at 1 over n, I can make the radius like 1 over n plus 1 or something. And that.
Put it at 0.
Okay, yes, so the neighborhood right at 0 is very weird, All right? The neighborhoods anywhere else are not so weird. They either look like this, or up here they look like, you know, one of these, right? But right at 0, that's a weird one. Can you describe in words what that neighborhood would look like? So I mean, if this is 0 here, it certainly has a piece of the horizontal part. What else would be included? Yeah, some verticals. How many verticals? I would say infinitely many verticals, right? If you are at the point 0, and any neighborhood of 0 must include infinitely many little vertical biddies, because these vertical lines approach 0. So the neighborhood of 0 is especially weird. It looks like this, something like that. I suppose if you really want to make it like a circular neighborhood, if you imagine, these go up, you know, higher and higher to a certain point, I guess, right? Remember, I drew them sort of ascending like that because, remember, I'm trying to imagine what it would look like if I intersect a ball from R2 with this weird comb shape. Yeah, great. Are there any other weird points where the neighborhood could look different? Actually, I can see one other type of neighborhood that you could get from here, which is less weird than that one that I just drew. But yeah.
I feel like a U that like intersects 2 lines.
I would say that will not happen in a basis neighborhood. If the neighborhood is big enough, you might get a U, but you can always shrink the neighborhood down to exclude the two ends. Whereas like at this point, even if you shrink the neighborhood down, it's still going to have all 3 parts to it. Anybody else see? Yeah.
You can put one at 1. We'll get a right angle.
Okay, yeah, you can get a right angle, so that's a little different. Actually, this is not what I was thinking of, but yeah. 1 is kind of special. It's the only one where you can get a right angle, all right? Anybody have another idea? I got one more idea. Maybe this won't seem very interesting to you, but how about at the end of the comb teeth? That looks like a vertical interval, but it includes the top point. So it looks like this, but it would actually include the point at the top. If I look at a neighborhood of a point at the top, you think of what would it look like if I had a little R2 ball around that neighborhood? It would include the top point plus some of the rest of it. So that one would look like this. That's like right here. Maybe I should try to include them all on my picture. All right, this is the infinite comb. It has a few different types of neighborhoods, basis neighborhoods that you could get. One is extremely weird, this one. The other ones are not so weird, I guess. All right, excellent. Would it change anything if we do include the line up the left side? What if we do include the line going up the left side? I'm gonna try and draw this again. Now it's still, I mean, you still get all that stuff that you can still see on the picture, but what if we also include the line at 0? All right? So also including the line at 0. I believe this now is a closed subset of R2. That was part of the homework that you did about this, was showing that the comb itself is not closed. I think when you add that line in, I believe now it is closed. But anyway, that's not what I'm trying to talk about. What do the neighborhoods look like now? Well, when I add that line in, it does actually modify the neighborhood around 0. So now the neighborhood around 0 looks a little bit different. It looks like this. But it actually does include a line on the end, right? There is, though, one other weird type of neighborhood that you can get in this example. weird type of open basis neighborhood. Yeah?
Is it on zero but like above?
Yeah, so what does a neighborhood look like to a point like this? This is what I want to think about. I think this actually may be something like what you were thinking of before. If you take a little ball around that point, it automatically must intersect infinitely many of the other lines. And so what a neighborhood of that point looks like, it would be this point and then a little open interval around that point, but then it also includes infinitely many open intervals nearby. This is quite weird. Something very weird about this is that that little neighborhood is disconnected. We're going to talk about that word topologically later on, but I hope you know what I mean by that, more or less, vaguely speaking. It's in like a bunch of different pieces. This is an example of a topological space where there are some points which have no connected neighborhood at all, which is very strange. Those points on the left line there, all neighborhoods of them are disconnected, which is, it's actually hard to come up with an example like that. All right, and then just for the sake of completeness, there's one more special type of point, and that would be the one on the top, the actual point in the corner on the left. That one, its neighborhoods would look like this, similar to that previous one, but infinitely many sort of half intervals, including the top points for all of them. This is what a neighborhood of this point here looks like. All right. Wild and crazy. The infinite comb. I think it's a cute example where like weird things can happen when you use the subspace topology. Any thoughts about that? All right, I got a couple less weird examples to in our remaining 8 minutes here. Less weird examples. Let's talk about subspaces of R. R1, right? How about everybody's, think about everybody's favorite subsets of R. How about Z? This is one, actually, we don't talk about Z very often in this class because topologically speaking, Z is not very interesting. Q is kind of interesting. We do talk about Q every so often, but and you'll see why in a moment. Z is not very interesting as a subspace of R. But anyway, so I'll draw a picture. Here's all of R, and then Z, of course, just looks like a bunch of individual points, evenly spaced, going on forever in both directions. I would like to think about what does a neighborhood in this look like, Z subset of R. For example, if I say, just look at that point right there, what does a basis neighborhood around that point look like in the subspace topology? Let's say this is the number 0, just for convenience when discussing it. A small neighborhood around 0 looks like, remember what you have to think, this is subspace topology, so you imagine what would it look like if I took a small neighborhood from R, but then you intersect it with Z. So a small neighborhood from R looks like a little open interval. Can anybody say what is the neighborhood of 0 going to look like? You imagine starting with the small neighborhood in R and then you intersect it with Z. The answer is maybe. Seems stupid? If it seems stupid to you, then you may be on the right track. Feeling stupid?
It would just
What?
be like a dots at each like integer.
Yeah, what about a small neighborhood around 0?
Would it just have 0 in it, depending on how?
Yeah, depending on how small it is. But if it's really small, I'm trying to imagine like a very small neighborhood around 0. That would exclude everything else, and it would just have 0 in it. You imagine you should be thinking about a small open interval from R, and then you intersect it with Z. But it's just going to have 0 in it. So a small neighborhood around 0 looks like that, just the set containing 0, all right? And this has nothing to do with 0 as a special number. Every number has this property. So in Z as a subspace, with the subspace topology, in Z as a subspace of R, the set, N is open for any N in Z, right? This topological space has the property that every point by itself is an open set. Does that sound familiar to anybody? Actually, this appeared, something like this happened on, I think, the first homework assignment. I don't know if you can remember that far back. You showed something about if you have a topological space where every point by itself is an open set, then automatically this means it is the discrete topology. That was something he proved. Just because any set can be written as a union of all of its points. And so the fact that each point individually is open means that every set is open. All right, so the conclusion is, so Z with the subspace topology, can I say, in Z, the subspace topology from R is the discrete topology. Remember, this means all sets are open. And this is regarded as sort of uninteresting, because if every set is an open set, then there's really not a lot that you can say about. I mean, everything interesting in topology is all about like which sets are open versus which sets are not open. But if everything is open, then there's nothing really for you to say about your set, topologically speaking. So this is why we usually don't talk about Z in topology, because Z as a subspace of R gets the discrete topology, and that makes it completely uninteresting as a topological space. All right. This also is why the word discrete topology is called discrete, because a space which is the discrete topology, it functions as if it were a space where just all the points were separated from each other. The points none of them are next to each other, none of them are nearby each other. They're all separated from each other. And that's what this word discrete means, like as an English word, discrete, it means things which are in isolated chunks, not this is the opposite of continuous, where things are nicely connected to one another. All right, so that's actually why discrete topology, the discrete topology. If you want to imagine, like if you approach me on the street and say, hey, I would like you to imagine a set with the discrete topology. What I imagine in my mind is just like a bunch of points that are far apart from each other, and none of them are connected up in any way. That's what the discrete topology always leads to. So the discrete topology makes a space of individual isolated points, like Z in R as a subset of R. All right. This is why the word discrete topology is used, because these points are none of them are near each other. All right. Can I say, we got 1 minute left. Let's just say, just to close it out here, how about Q? This one we do talk about. Q as a subspace of R. This one turns out not to be the discrete topology. Q, of course, looks like, it's sort of it has points everywhere, but not every point is in Q. What does a small neighborhood look like? Well, in Q, it looks like a real interval intersected with Q, right? That's what a neighborhood in the subspace topology looks like. It looks like a neighborhood from R, which is being intersected with Q. So this is just, there's not much more to say about what that is. It's just an interval of points, but you only use the rational points in there. All right. This is not the discrete topology. It is not true that an individual point by itself is an open set, because every point, an open set around any point also includes all the nearby rationals, which is not true of Z, right? An open set around this point can exclude every other integer, but that can't happen here. An open set around a particular point must automatically include lots of other rational numbers. So this is, can I just say, it's not discrete. It's not anything else that we recognize either. It is what it is. This is Q with the subspace topology. There's no other way to say it. All right, that'll do for now. Thank you for your attention. Check out the homework. We will have homework over the weekend. I am planning on posting it sometime this afternoon. Probably shorter than last week's assignment, but that'll do it. All right, have a good weekend.